I think page 99 is what I said. And I'll start with the screen share here. I think we're streaming now. So let's start up with a screen share really quick. Whoops, not emails. This one. So here we go. All right, so we're talking about friction. Okay, and so this is again page 99 up here, page 99. So friction is pretty complicated. Notice you see this word relative motion, which is something we discussed in chapter 4. So basically, so there's a bunch of words here that you can read. I know that you can read, so I don't want to go through all this right now, but there's two things that I want to talk about. One is the different possible equations that can be used for friction, and that's discussed right here at the top of the page. A few points worth emphasizing. And then, which way does friction point? Shouldn't it be obvious? Evidently not. After teaching this class for many years, it is not obvious to students at first. I don't know, Jay, do you agree that, I don't know, or not agree? What do you have to say about friction, and do you have any advice for them as they enter the world of friction?
Definitely that it's not always opposite acceleration. That's something that I assumed right off the bat, but that's not the case.
It's true about half the time.
Oh, half the time, that's true, but half the time you're wrong. So
yes. So how would you describe it? How do you figure out which way friction points in a problem, Jay? And let me make you the speaker for fun. Let you do my job.
Well, how I figure out is I figure out which way it's traveling. So the motion of it. So the velocity in this case, not the acceleration. And I do friction in the opposite of the velocity.
Oh, so let me give you one, Jay. So, of course, oops, not that. I needed to do this one. So I'm going to put Jay on the spot now. All right, Jay. So let's say we have a block here. And so here it is. Let's say we have another block on top of it. So this is object 1 and this is object 2. All right. And so Jay knows what she just misspoke. Technically, she didn't say it correctly. She said it correctly for most cases, but not all. And she knows it. So let's say I'm pulling this way, right? Now, oh, whoops, let me, there we go. I was getting a lot of glare there. All right, so in this case, Jay, walk me through, and let's say there's a surface right here, and then there's a surface up here, and let's say we're just pulling these two blocks along. All right, so I'm pulling them this way, and to be clear, this would look exactly like this scenario. I have a book here, and I have an eraser on top, and I just pull it along. So this is not an absurd situation. I have a bottom block that has a big mass and an upper block that has a small mass. And instead of, just so I could fit this on the screen, instead of pulling it, I'm pushing it to the right. So it's exactly the same as this, right? So Jay, walk me through what you're thinking in your mind as we try to figure out the friction. And
the first thing I think of is that you're moving block 2 with the tension, you're moving that to the right.
So 2 is moving to the right. What does that tell you?
Mm-hmm. That's telling me that the friction is going the opposite direction of the motion for 2. So it's going to the left.
On which surface? Here or there?
On the bottom surface.
Okay, so on this surface, she's saying 2 is trying to move this way of 2 relative to the floor. 2 is moving to the right relative to the floor. So she says friction is back, and she is correct. How do we analyze up here, Jay? How would you describe it?
I would describe it as block 1 wants to stay in the same place that it was. It doesn't want to go with
relative
block 2.
To what? Oh, okay. Block 2, or wait, you said block 1 wishes to stay at rest.
Relative to the Earth.
Rel to Earth. Okay, and so I'm cool with anthropomorphizing. I can't say it right now. Basically giving feelings to the block one. Let's just do that. Even though blocks don't have feelings, I'm totally with you. I say it all the time. Block one wants to stay at rest. It has no feelings, but yeah, whatever. Okay. So how does that help you?
Well, that tells me that if block 2 is moving to the right and block 1 wants to stay at the position it's in, block 1 is going to resist the movement to the right.
Okay, wait, let me write this down. Block 1, I'm going to use the word tends. It may not be able to successfully resist the motion to the right, but it would try. Tends to resist motion to the right. So what does that tell you?
Technically, relative to block 2, you can think of block 1 tending to move to the left, though it's not actually moving.
It is moving. Which way is it moving?
It's moving to the right.
Yeah. But it's tending to resist motion to the right. Agreed?
Mm-hmm.
So like what she's saying, if block 1 had its way, it would move to the left relative to the 2, to block 2. It doesn't, but it wishes it could. Okay, so what does that tell you, Jay?
That tells me that friction between block 1 and block 2 on block 1 is moving to the right.
It feels very uncomfortable drawing this. Like, I'm like, oh, it's moving to the right. I almost drew it backwards too, even though, whoa, but I did write on my shirt. So there's karma. All right. So what's a good name for this? What would you call this? Friction. We can't have the same symbol because it's not the same size. So what might you call this one, Jay?
I used to call it F1 on 2.
Yeah, I would do that too. And then we could call this just friction 2. That way, this is 2 with the floor, but then I don't write the subscript for floor. All right, very good. So what does that tell you about block 2? Is there any other friction on block 2, Jay? Actually, you're good, Jay. Let's make some other student tell me. Some other student. Right. Well, okay. Yeah, never mind. Whatever. But block 2 up here. If there's a friction 1, 2 to the right on 1, what does that tell us about block 2? Somebody else, not Jay.
To the left.
Yes. By what principle?
Action reaction.
Yeah, Newton's third law. Nice job. And what we see here is it's very, very complicated to correctly state words about friction problems. So we have to be very careful. And then, to be honest, Jay is really good at this. But even Jay, who is really good at this, even I, who am really good at this, we struggle to say the words correctly. You have to be very precise when you speak about friction. So sometimes, rather than trying to say all these words, it's a lot easier to communicate with a free body diagram. And so the free body diagram, a picture is worth 1,000 words. It's probably worth 2,000 because you don't have to talk about all these words anymore. So for me, that's, yeah. So notice what Jay said initially. She originally said friction opposes the direction of motion. That is not correct. Friction opposes the tendency of relative motion would be a correct statement. So look at this. I just want to point this out. Friction does not oppose the motion of 1. 1 is moving to the right, just like this, right? The eraser's moving that way because friction between the blocks forces it to keep moving. If there was no friction, it would fall off the back. Ah, geez, sorry, I'm having some trouble here. If there was no friction, it would just fall off the back like that. Because it's tending to move to the back relative to the book, there's friction forwards on it that keeps it from sliding backwards relative to the book. It's extremely annoying, and there's no easy way out of that. Everybody, let's give Jay a round of applause there for putting up with that. Nice job, Jay.
So
questions from the students? Yes.
Yeah, I have a question. So when something stays in place on an object that's moving, like in this situation, does
Mhm.
that mean the frictional forces are balanced out and like, or the forces are balanced out from like left to right? Is that what's like keeping it
No,
in place?
no, it's not staying in place. Look at this. Watch this picture. Is the eraser staying in one place?
No. Oh yeah. Well, I meant like staying on top of the
You mean staying
handle.
in place relative to the book?
Yes.
And so we got to, there's no way around it. If you say it wrong, I'm going to call you on it. So we've
Okay.
got to really work on saying, you mean staying in place relative to the other object, then I would agree with you. You see where I'm going with that?
Yeah. So that
I'm
means
trying to be
balance.
ruthless here just so you get the habit right.
Yeah.
Yeah. Is that cool?
Yeah. So that does mean that which forces are balanced? The frictional forces on.
So now here, these are an internal force. They're an action-reaction pair. They're equal and opposite in magnitude, but they're on different objects. They can't balance.
Oh.
Forces on a single object can balance, but action-reaction pairs occur on different objects. They can be equal and opposite, but they can't balance out because they're on different objects. You see where I'm going with that?
Oh yeah.
That's why I don't like what you were saying there technically. Is that good?
Yeah. So what would you say like is keeping the object in place relative to, or keeping the marker in place relative to
We
the
would
book?
say these two blocks are friction coupled. So what does that mean? They're coupled. So I don't know if you could think of this, but like imagine two train cars, they come together and they link. We call that a coupling. So that would be a mechanical coupling. These would be frictionally coupled. The friction is what's keeping the two blocks together.
Yeah.
Because, yeah. So now I could show you an example where there's not enough friction to couple them. Watch this. All I have to do is move it and jerk it fast enough. If the acceleration is too large, if I apply too much force, the friction is insufficient to keep them coupled. Is that helping?
Yes.
Yeah. So, yeah. So notice the same problem, depending on how much force you apply, the friction could keep them together or it could be insufficient to keep them together. Yeah. All right. So, whoa, that was a lot of stuff. Now, I want to show you actually some equations that relate to this on the screen here. So let's go. So actually, I just talked about this. We're going to do this over and over and over again because you can't learn this without. So this is how I say it down here, a summary of what we just did. I like to think of it this way. First, consider the relative motion or tendency to move between two objects. Maybe they don't actually move, but think about the tendency. And so here is all the logic that we just went through for that problem talked out. So I'm going to leave that there for you to look at later. Stick with me now. We've only got 10 minutes left. I want to try and at least do one problem today. So in this case, here are the different cases, okay? If the objects are in relative motion, we're going to use this equation. Friction is mu. This symbol right here is called a mu. The subscript K means kinetic. N is the normal force. So it turns out usually the more normal force you have, the more friction you have if things are in relative motion. If they're not in relative motion, this is why it gets so tricky. Again, this is like the upper block. If we move these and block 1 is not moving relative to 2, it gets nasty. Then we have one of these two cases. If it's just about to slip, we say it's mu static times the normal force. If you see a problem that mentions it's just about to slip, or it says the minimum something to prevent slipping, or without sliding largest, or something like that, those are the keywords in a problem that let us use this equation. Finally, some problems do not indicate it. And then I just say F is what it is. Resist the temptation to assume this. Just because it's not moving doesn't mean you can use static friction. That subscript S means static friction. So it turns out it's actually less than that value. All right. So let me give you a quick example here with our stupid eraser problem here. I might need to get that back. Here's my eraser. Here's my book. Right now, let me get out of the way. Right now, the eraser, and let me get this background clean. just so you can see a little better. This is our last topic we got to figure out. There's my block. Right now, how much friction do I need right now at this instant to keep the eraser from flying off the book if I could hold my hand steady?
None.
None. How about now? A little or a lot?
Little.
It's not slipping yet. It's not slipping. At some angle, it's going to be just about to slip. Hold on. Well, there it is. So at this angle, it was just about to slip. Sorry, if I could show you the board a little bit. Oh, gosh. Sorry, it's hard to do this. Let me, if I was right about at that angle, it was about to slip. I don't know if you noticed that. So for angles less than that, it's not about to slip. For angles more than that, it is slipping. For this angle, it was just about to start slipping. So here's the idea. Oops. Where'd that marker go? Well, let's use another one. Okay. The idea here is, here's how you write these symbols. F is going to be friction. That's the frictional force. And sometimes we get lazy and call it friction. Mu is called a coefficient of friction. So here's how you draw a mu, everybody. Draw the letter U and then put a line on it. Draw the letter U, put a line on it. Okay? Mu is called a coefficient of friction. It is not friction. If you're sliding relative to surface, we say friction is equal to mu kinetic times the normal force. This is called the coefficient of kinetic friction. I'm going to pause. Get that glare out of there. Okay, so F is friction, frictional force. Mu is not friction. Mu is the coefficient of friction. If you're sliding, we would call it the kinetic coefficient of friction, or the coefficient of kinetic friction. So again, to draw your mu, draw U, put a letter down. Okay, it's not U. But if you think about it, I know this seems cheesy. Look at this. Doesn't friction look like a lot of fun? F-U-N. This is how you can remember it. Friction is fun. And then draw a line. Friction looks like a lot of fun, and then draw a line. I don't know if that works for you. All right, let's keep going. If about to slip, or sometimes we say on the verge of slipping. If you see these words on the verge, that means friction is equal to mu static times the normal force. Whoops. Okay. So that's a static coefficient. Otherwise, friction is just some value F. And we can't relate it to the normal force. Notice what's special about this here, people. This is a very special thing to use. It turns out the amount of friction usually relates to the normal force, not always. Let me give you a counterexample one more time. Let's say this is about 100 grams, okay? Well, if mass is 100 grams and G is about 10, I hope you agree this is about 1 Newton. Right now, I'm going to put that on top of here. What is the normal force exerted by the book on this eraser? The weight is 1 Newton down, so the normal force is?
1 Newton.
And how much is the friction? in newtons?
Is it 1 Newton?
0. I don't need any friction right now, right? It's
Yeah.
not moving. It's not tending to move. There's no friction required to keep this. So here's the idea is sometimes friction is less than mu static times the normal force. And here's one example. If it's not moving at all and you don't need any friction, clearly friction is less than that number. All right. Okay. Let me give you an example again. Let's go to a simulation. Whoops. Oops, here it is. Okay, I'm going to apply a force. Let's just say 300 newtons. Now, I just want to point this out. Right at this moment, there's 300 newtons this way. Now, I could see that this cart is 100 kilograms down here. So what's the gravitational force? mg. I'm going to cheat. Let's just say g is equal to 10, everybody. Let's say g is equal to 10. So I hope you agree this is about, well, actually g is, we could do this. It's just 980. That's actually easier to do here, right? Because it's 100 times 9.8. That's going to be 980 newtons. Right now, what is the normal force? Oh, they can't see that at all. The normal force should also be 980 newtons, right? Now, what is the acceleration at this instant in time? It's actually active. How much is it accelerating? None.
Yo, they're blowing me up. They're about to blow me up.
What's that?
I'm fleeing. I'm fleeing. Using a
Okay.
medikit? I'm using a medikit. No, I'm
This man's out here playing Call of Duty right now.
I'm
man.
stacked. Oh shit. Yo, these guys are tryhards. Oh my god.
All right. I don't know what's going on.
Dude.
Yo, Edgar, you're not muted, man.
Edgar, you're not muted.
Uh-oh.
That's all right. That's fine. Dude, you don't have to come to class. You know, you can just skip and watch the live stream if you got to get that in there. It doesn't bother me, man. Just whatever. All right. So, all right. That's cool. Whatever. So at this point, what is the frictional force in newtons?
Is it 300?
Yeah, 300. All right. Let's try and get through this. Sorry if maybe I'm going too slow here, but I don't want to screw you guys up. All right. So my apologies.
Don't worry about it. Don't
Yeah.
worry about it. What the
All right. All right. That's cool. All right. So in this case, I just want to point out we have these weird new equations for friction. Now look down here. Right down here, notice mu kinetic is 0.3 and mu static is 0.5. The normal force is 980. So let's say F static, let's just plug in mu static times the normal force. When I punch that in into my calculator, I get 0.5 times 980. So that's 490. That is the maximum possible amount of friction that this surface can provide. All right. Okay. And what if I do mu kinetic times the normal force? Well, that would be 0.3. I got to punch that in on my calculator. 0.3 times 980 is what? 0.3 times 980. What is that? 294, I think. All right. So we got 294 there. All right. So I just want to point out right now, the frictional force is not equal to either of those numbers. And in fact, what if I jack this thing up to 350, right? Well, if I jack this up to 350, it's clearly not any of these numbers. Let me get my eraser really quick. I should have picked a different number here. If I do 350, I just want to point out that this one is 350. This one is 350. And it's neither one of these numbers up here or up here. So these two equations are great, but they do not always apply. This is the scenario in your workbook on page 99 where it says it's not on the verge of slipping. It's not slipping. It's just some other number. All right. So right here, it's not about to slip. Help me out. What number would I need to type in for the applied force to put this thing on the verge of slipping? Let's say I want to make this thing on the verge of slipping.
Is it anything above 490?
It should be anything above 490. So if I go in here, let me get in, zoom. Let's say I go in here and I type 489, it's not going to slip. If I type in 490, it's not going to slip. However, if I type in 491 and as soon as I hit enter, what should happen?
It should go really fast.
It will not go really fast.
Oh.
However, is this going to exceed the maximum possible amount of friction? Yes.
Yes.
So what happens here is it didn't go really fast, but it did start accelerating. So at that instant, this is no longer true. This is no longer true. As soon as you apply more than 491, this situation means we've switched to kinetic friction. So if I could clear this all and run this again, let's return the object here. Whoops. Oh, let me get this out of here. Okay, return the object. All right, so I'm going to put it here at 0. Oops. All right, let's just start right here. So again, what I'm going to do is apply 491. When I hit enter, right, we expect there should be some friction. But right now, think about it. This is 491. We've exceeded the maximum possible amount of friction. As a result, it actually starts to slide. As soon as it's sliding, this one becomes that 294 number. This 294, if you remember, was mu kinetic times the normal force. And I guess there's a newtons in there, sorry. So that's what's tricky about this problem. Now, I was hoping to get through more on this one, but it turns out we've covered most of the details of this problem. I want to point something out here in the solutions here. We just did 6.1. Now, notice the numbers that I used are a little bit different. In 6.1, I used a 1 kilogram block instead of 100, but I used the same coefficients of friction here. And you'll notice the number, instead of 491, now I get 4.91. So what you could do is you could do 6.1 at home and learn about this. And maybe I'll foreshadow this a little bit. So here it is. What I did is the first thing I needed to do was figure out, I know we're running a little late here. Sorry about this. I needed to figure out the amount of friction, the force that puts this on the block of, on the verge of slipping. So I said, okay, anytime I exceed this amount, if you're wondering, how did I get the normal force? Well, the normal force is equal to mg because there's no acceleration. So that gives me this value. That's how I got this number. So now if I'm at any other number, I know it's not going to accelerate. Great. Once it starts sliding, if I apply 4.91, this is my frictional force. Then I just do an FBD and figure out the acceleration. And notice these crazy looking things. I don't know if this makes sense to you now or not. The idea is, as you push harder, I'm pushing with 2 newtons, 4 newtons. So here's that special, this is 4.91 or 491 if we had a 100 kilogram box. Right? So once we hit that point, friction drops down to this constant level. Everywhere before that, friction is less than 4.91, less than 4.91, less than 4.91. Right when I get to here, as soon as you apply more force than 4.91, it's going to slip and your friction slips down to this 2.94. Notice what happens to the acceleration. No matter how much force you apply, it's not going to slip until you hit 4.91. As soon as you hit 4.91, all of a sudden it's accelerating and it starts moving. All right, so let's call that good. You guys could look at that problem. And you could try to do the next problem too. Let me show you the next problem. Sorry, I'm just slow today. Let me show you one last thing and I'll let you go. I hate keeping you late. Sorry about that. I'm not going to do this whole problem, but I just want to point out you should be able to do this problem next. All it is it's the same exact problem, but now the force equations are going to be a little bit different because the force is applied at an angle. And you could, in theory, do this one now or this one. And at this point, in theory, you could do the whole chapter. We're going to need to do a lot of practice. Let's